In this video, we're going to talk about something a very important aspect of numbers and measurements known as significant figures. So like I talked about in the last video, we have to remember that every number that we work with in this course, or every number that we work with really in science in general, represents a measurement of some sort. And along with that, we have to remember that a measurement is only going to be as accurate, is only going to be as good as the measuring device that we actually used for that measurement. And so, for instance, this measuring device here, oop, killing me slides. There we go. This measurement device here is only able to measure this balance, only measures to the 10th spot. Whereas this balance here can measure all the way out to the 10,000th spot. Much, much, much more accurate balance. And so what that really means, and these are weighing two different things here, two different amounts. But if we look, for instance, if we consider that first measurement, if we consider that 10.4. So again, since we can only measure to the 10th spot with that particular scale, that particular measuring device, and I always do this, shrink down a little more so you can see my screen. So this particular balance here can only measure to the 10th spot. Incidentally, the ability to measure out more accurately like this is reflected in the price. This balance here, you can probably buy this for 50, 60 bucks. This one here, 5 or 6 grand, easily. And so there's a big difference in the accuracy of those, big difference in their price. But this one here, that can only measure to the 10th spot, we know then that realistically, this measurement is anywhere between 10.35 or 10.44. Anything that's within that range between those two is going to round up to 10.44. And so the real amount, the actual mass of this, let's say we were able to measure it on this other balance going out to 4 decimal places. I mean, the real mass might be 10.3564. That's going to round to 10.4 on this balance. It could be 10.4412. That's going to round to 10.4. And so there's that big range there of what the number could actually be. This means that if we're performing calculations with measurements, we have to consider the accuracy of our measuring device when we report our answer. Let's look at another example. Let's say we're trying to find the density of something. We're not going to work much with density in lecture, but it's definitely in your book, and some density calculations are part of your homework. To find the density of anything, it's our mass divided by our volume. And so let's say we have a particular balance that measures the mass of our object to be 5.4 grams. We measure the volume of this object to be 120.2 milliliters. And so again, we have to remember that this mass realistically could be anything between 5.35 grams or 5.44 grams. And so let's look at the range, or let's look first at just performing our calculation. Our 5.4 grams divided by 120.2 milliliters. We plug this into our calculator, and let's look at all the digits our calculator gives us. 0.0449251248 grams per milliliter. So our calculator is going to give us all of those digits. Adjust things a little bit here so we can see. There we go. But again, this 5.4 really could be anything in that range. And so if the mass was really 5.35, and we work with that, That's going to return us a number of 0 0.0. See if I can fit all this in. 44509 1514. Include our units, grams per milliliter. If the actual mass was 5.44, that would give us 0.0452579035. And so we know that the real mass is somewhere between these two numbers. And that's as much certainty as we can really have, is it is between those two. Our calculator, however, is going to return this to us. And so we have to think about, is it fair for us to report our answer like this? And the answer to that question is no. We can't report this as our answer, because if we're reporting this as our answer, we're saying that we know without a shadow of a doubt, we know for a fact that the density of this object is something that we know accurately out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. But we don't know that. What we know for sure is that the density of this object is between these two numbers. And so what we have to do is account for how many what we call significant figures there are in our measurements. And our final answer will only be reported out to the lowest number of significant figures that were in our initial measurements. And we'll talk about how to determine how many significant figures there are in just a second. But in this measurement here, there are 2 significant figures. In this measurement, there are 4. And so our lowest measurement has 2 significant figures. And so our answer is going to be rounded to 2 significant figures. And so we're going to round off our answer to 0.045 grams per milliliter. Now we are reporting an answer that is fair, that reflects the accuracy of our measuring devices. If instead we were able to measure this out to 3 significant figures at 5.40, then we would change what we rounded our answer to. We would instead round it to 3 significant figures, would be 0.0449 grams per milliliter. And so we will always use the number of significant figures in our measurements to determine where to round our answer off. And so that brings up the big question, well, how do we determine how many significant figures there are in a measurement? We do that by using these rules. And so if it's an actual number, and so what we have to do is count up in our measurements how many significant figures are in that measurement itself. And so when we're doing that, all non-zeros are what we call significant. And so in this example here, 1.234, these are all non-zero digits. So we would consider these all to be significant. And there are 1, 2, 3, 4 of them. So there are 4 significant figures in this measurement. And so the trick then comes in identifying zeros as either significant or not significant. And so we'll use this set of rules. And this picture is right from your textbook. I'm finding that I really love a lot of the diagrams and tables in your book in particular. And I'm going to steal them for some other classes because this is a great graphic for significant figures. Sometimes called sig figs, by the way. You'll hear me abbreviate sig figs quite often. And so zeros. If you have a 0 between non-zero digits, that is significant, regardless of if there's a decimal in the middle or not. Doesn't matter. So right here, 3.05. Here's a 0 in between 2 other non-zeros. That means that this 0 is absolutely significant. And so there are 3 significant figures in this measurement. 2006, 2 zeros in between 2 non-zero digits. And so these zeros count. 1, 2, 3, 4, 4 significant figures, significant digits. As we go through the rest of these, what I want you to keep in mind is, does this 0 reflect part of the actual measurement itself? Or is it what we would call just a placeholder zero that tells me where a true measurement begins or ends? And so does this zero help reflect the accuracy of the measuring device or not? And so that brings us to this one. Zeros are significant. All these up top here represent zeros that are significant. Of a zero to the right of a non-zero in a number containing a decimal. And so if you've got anything that contains a decimal, these would be what we'd call either leading zeros or trailing zeros. And so a zero to the right, or of any number, sorry, that includes a decimal, is significant. So numbers in pink are not significant, numbers in blue are. And so we have zeros here, but these are to the left, which we'll get to down here. The zeros to the right, however, those absolutely are significant. And so we have a non-zero here and two zeros that are to the right of a non-zero and here. And so let's just take a look at that and consider this for just a second. And so again, remembering that these represent measurements of some sort. If I have a measurement that's simply, I'll say 22 grams versus 22.0 grams. Now, yes, mathematically, these numbers are identical, but this isn't math operations that we're doing. These numbers are measurements. And so a measurement, when we're reading measurements, a zero like this tells us that not only do I know to the ones place, I definitely know this measurement to the tenths place without a shadow of a doubt. And so remembering that this 22, realistically, if we're measuring on a balance, if we're measuring on a scale, that 22 could be anywhere between 21.5 or 22.4. It's anywhere within that range because the last digit is as close as we can measure, and everything would be rounded up or down to get to our 22. Here we're saying, okay, I know it's actually 22.0, meaning that the real measurement here is anywhere between, we would say, 21.95 to 22.04. And so we know the measurement much more accurately. And so this zero gives us more information that is reflective of the accuracy of our measuring device. That's what makes it significant. That's what makes it a significant digit. And so a decimal that is placed after one or more zeros indicate that zero is significant. So like in this example here, we have some what we would call trailing zeros after our non-zero digits, but this decimal point is a way for us to show that these zeros actually mean something. These zeros are significant. And so in this case, I definitely know this measurement to the ones spot very accurately. In this measurement, I only know the actual measurement to the thousands spot very accurately. So big difference in the accuracy of these two measurements. So this one would have 5 significant figures and this one would only have 2. When you express numbers in scientific notation, all of the numbers expressed there are significant. And so this zero is absolutely significant. That's one of the other reasons to use scientific notation. And so if we were to look at these two numbers here, we could express those differently in scientific notation. The first one would be expressed as 1.1000 times 10 to the, how many places are we moving? 1, 2, 3, 4. So times 10 to the 4th versus 1.1 times 10 to the 4th. Again, mathematically equivalent numbers. But this one demonstrates a much more accurate measuring device than this one does. If we're looking at zeros that are not significant, examples are for anything less than 1, the leading zeros, we would call them. The zeros between the decimal and the non-zero are just placeholders. So these zeros are not significant. And so each of these measurements would only have 2 significant figures. For trailing zeros, for numbers greater than 1, the zeros that are following the non-zero digit are also not significant if there's no decimal point there. Remember, that decimal point makes a difference, but if it's not there, then those zeros are not significant. And so this isn't necessarily intuitive stuff. If you've never worked with significant figures before, it's not something that you can necessarily look at and just say, oh yeah, that makes sense, I get it. Work with us a little bit, think about it. Remember that these numbers represent measurements. And so we have to somehow represent the accuracy of those measuring devices. And so all of this, all these significant figure rules apply to measurements, which are going to be different from exact numbers that are obtained by counting. And so if I'm counting, for instance, the number of pens on my desk, I've got 3 pens on my desk right now because you never know what color I might want. So I've got a red, a blue, and a green. And so that's exact. There's no uncertainty there. And so if you're ever using counted numbers, they have technically an infinite number of significant figures. Really just means that we don't take significant figures into account with anything with counted numbers. An example would maybe be taking the average. Let's say I want to take the average of 3 different numbers. Taking the average of maybe, we'll make it easy, the average of 10.0, 20.0, and 30.0. So to take the average of those, I'm going to add them all up. I add them all up and I get 60.0. I'm then going to divide that by 3. And I'm going to get an answer of 20. Now I'm going to look to my significant figures and say that so normally I would look at this and round my answer accordingly, but I'm going to ignore this 3. I'm not going to consider this 3 in looking at my significant figures because this is a counted number. I'm counting 1, 2, 3 measurements, so this is exact. And so I'm going to report this answer as 20.0 for my average. Now let's look at how we actually use significant figures. So anytime we're doing a calculation, we need to determine the significant figures that we're going to use for our final answer. If in our calculation we are multiplying or dividing, our final calculated answer cannot have more significant figures than the measurement with the fewest number. And so essentially, just look at all your different measurements, determine which one has the lowest number of significant figures, and that's how many significant figures to report your answer to. And so again, sort of back to our density example. If I have, just to make numbers up, maybe 22.4 grams divided by 10.0 milliliters. Actually, I don't want to use 10.0 for reasons. Maybe 9.50 milliliters. And so I plug this into my calculator, and I get 22.4 divided by 9.50, and my calculator spits out 2.357894737. So now I look back to my actual measurements. 1, 2, 3 significant figures here. 1, 2. Is this 0 significant? It is. So 1, 2, 3. Both of these measurements have 3 significant figures. And so I'm going to round my answer off to 3 significant figures. 1, 2, 3. I'm going to use standard rounding rules. And so the number after the 5 is a 7. And so I'm going to round this answer off to 2.36 grams per milliliter. Now let's say instead I had 22.4 grams and I only knew this to the tenths, 9.5 milliliters. 1, 2, 3 significant figures, 1, 2. So now I'm going to round my answer off to 2 significant figures. And so I'm instead going to have an answer of 2.4 grams per milliliter. So that's what we do for multiplying or dividing. Adding and subtracting is a little bit different. With adding and subtracting, we look to see how many places our decimal, or how many places past the decimal point our measurement goes. And our final answer will go no further than our lowest measurement. Let's take a look at what that means. Let's say we're adding up 3 different lengths. 11.24 meters, 12.672 meters, and 13.1 meters. Excuse me. Okay, so we're adding all these numbers up. See if I can do some math in my head here. We get 2, 11, 12, we get 1, 3, 9, 10, 1, 2, 4, 7, 3. Here's our decimal point right there. And so now what we need to look at is how far out does our measurement that goes the least past the decimal point, how far does that go? And we see that our final measurement here only goes to the 10th spot. And so that's where we're going to cut off our significant figures. And so we would report this as 37.0 meters. Now, hopefully some of you are asking in our last example for this video, but Professor Staples, what if I'm performing a calculation where I'm both adding and subtracting? Great question. Follow your order of operations, round accordingly through each step. And so let's say, for instance, that you're doing, for whatever reason, whatever the calculation might be, 2.20 plus 3.4, all divided by 6. Yeah, I'll just say divided by 6. There we go. So we're going to do our, within our parentheses first, 2.20 plus 3.4. We get 5.60. We're now going to round this accordingly before we use it. So we're going to round this to 5.6. So now we're going to have 5.6 divided by 6. We put that into our calculator. And we get 3 repeating. So we get this. And then we look to this calculation and we see 2 significant figures and 1 significant figure. So that's how we're going to round our final answer, is to 1 significant figure. And so our final answer to this whole entire calculation would be reported as 0.9. And then whatever appropriate units we had that we were working with. That's significant figures. And so practice it. There is some practice with this on the website. So if you go, again, we're here on our materials page. We have a good significant figures practice worksheet with some examples there. So I would highly recommend that you use this to help practice and master this concept. Thank you for watching.